It's good to be back. Thanks for the return invitation. Clearly, people were suitably gripped by the previous subject matter, so I thought I'd bring two friends along from the adhesion research community to elaborate a little bit further on what I covered, what is now 2.5 years ago, which shows how quickly time goes by. But hopefully, you'll be positively surprised by some of the developments that have happened in the adhesion research world since the last presentation. Unfortunately, I must admit, because we have had some quite severe incidents on this subject across the network. So I'll come on to that in a little bit more detail. So just to pick up where we last left off. So what is the rail wheel interface? Just a reminder, we're talking very much about our ability to control a rail vehicle both under traction and braking when there is some contamination on the track. In the rail wheel interface, which, as I'm sure we're all aware, is the point of contact between the wheel and the rail, often no bigger than a 5p coin. But of course, there is so much more to it. If only it was so easy. I showed this last time. It's just a reminder of what can happen. So this is actually a photo of one of the first people on site at Salisbury, the line that was affected by, of course, what ended up being quite a severe low adhesion related incident. Unfortunately, we did cause life-changing injury, because in the industry, we obviously working to try to resolve these issues, unfortunately, don't always get it right. And that's why adhesion research is such an important topic. What did we talk about last time? We spoke quite a lot about sound, because that was a very active work stream at the time. Now, something that we'll forever grapple with and are still trying to optimize. Well, oh, I see. They're not on. All good now?
Yeah, that's good.
So we spoke about sound last time. There's some work that we'll come on to that very much covers the developments of some of the technologies that we introduced. But this is something we're still talking about, and it certainly isn't the magic solution to everything. We also spoke about leaf layer testing, so trying to simulate what a leaf layer, in terms of the sort of leaf layer that would cause what happened at Salisbury, which I'm sure we're all aware of, and what would result from that, and ultimately how we can then understand the chemistry to help to understand the mitigations. But again, there's a lot more to adhesion research than that. So that's ultimately what I want to come on to today. So taking into account what has been done in the past and what is ongoing at the moment, where do we go from here? How do we actually genuinely get a grip, excuse the pun, on low adhesion and ultimately produce a seasonally agnostic train that isn't affected by the external factors that affect low adhesion? So in ALG, I mean, it's an area of work that I've been leading, but ultimately we're looking at creating an adhesion expert train. So that's a train that is intelligently able to monitor its surroundings, but also do something about it. And there are many work streams going on, but I thought I'd select 5, and Roger and Rob are going to reflect on some other ones outside of this, but where there is actually a lot of overlap. And I know Roger was heavily involved in one of them. But ultimately, we're looking at in-service low adhesion monitoring. So that's being able to track low adhesion by actually measuring low adhesion values, calculating them in real time. We're looking at monitoring vegetation by some of the more intelligent technologies that we have available now, such as LiDAR and artificial intelligence. We're looking at railhead monitoring, so that's effectively tracking the condition of the railhead with high resolution photography. We're looking at intelligent data analysis and output, arguably the most important, because it brings all these data sets together and produces a meaningful output from them. And then we're looking back to 2 historic projects, one of which I co-supervised Roger, which was looking at understanding leaf effective low adhesion and creating a low adhesion forecasting model, which our vision is to incorporate a lot of these extra inputs that we're developing at the moment to produce something that is much more unified and useful. And then also there is very much the maths and the science behind everything, which is something that Loughborough have led in the past, but that we're ultimately looking to pick up again, using some of the values that come out of, for example, the low adhesion monitoring tool to validate the historic models, the academic models that have been developed. So this is a photo from July last year at the Chiltern and Princess Risborough Railway. We're very lucky at Chiltern because we have a local test track effectively, and they're always very kind and willing to supervise our testing activities. So generally, when we try to trial a new piece of technology, we can just give them a call, and with fairly little notice, we've got access to 4 miles worth of railway. So that's very useful. Why did we make use of that this summer? Because of the low adhesion monitoring mod. So this is a schematic of a Class 165 vehicle. I won't go into too much detail because we're more interested in what it does in this forum. But ultimately, subject to fitting a modem with a GPS in the cab roof, as well as a few wiring modifications, modifying the dump valves with a pressure transducer, and a slight modification to the wheel slip protection, the WSP rack. We're able to measure adhesion in live time to a very, very high degree of resolution. So that shows very much the same thing. Again, these slides will be available for your perusal in your own time if you're interested in any of the detail, and please get in contact with me if you have any specific questions. So coming on to the really interesting stuff. So this was the dynamic testing at Chiltern and Princess Risborough. So we very much tried to mimic, as per the industry standard, leaf layer testing. We didn't have to actually prove any attestation, but we did it to as close a standard to what you would require to commission a brand new WSP system as possible, incorporating paper tape, incorporating various levels of moisture and various speeds and brake step applications. And ultimately, we were able to prove the concept of the system that we developed, and we got some really useful WSP data, which gave us the assurance that when the unit went back into service, that it would generate the data that we were looking for. The main issue actually on this day was signal coverage. So we happened to choose the one bit of test track which appeared the most open, which was closest to a level crossing and had a car park next to it, but it was the only black spot on the entire test track. So often that's how these things work. This is a short video. I'm not sure if we'll be able to have any sound, but it's really just for demonstration. Sure we can hear anything, but I can commentate on what it is intended to show. So this is basically the train performing quite a significant slide, and you can hear the dump valves and effectively the wheels dancing, which is what they do when the WSP system activates. We're trying to stop the wheels from locking up. We're reducing the amount of uncontrolled slip and slide, and thereby preventing wheel damage and, of course, bringing the train to a safe stop. So what does the modification actually show us? This is a high-level view of the entire Chiltern network as of the start of October. So this is 1 month worth of data capturing. And we can see that we've had slip activity and slide activity across the entire network. So often where we wouldn't expect it, we've had wheels slide coming out of Marylebone where there aren't any trees. But it just goes to show, and this is a work stream that Rob and Roger will cover, that non-visible contamination can be an issue. So all of a sudden, this modification is telling us things about our network that we never knew. So a case study in question, we've got a rather substantial wheel slide into Warwick Parkway, which we've had several repeated instances of since. And I'm not sure how clearly we can see this, but these are the graphics that the modification produces. So we've got axle speed on every car. We've got brake cylinder pressure on every car, which is very much the raw data that is fed into the WSP system, processed, and then ultimately outputs what we're really interested in. Again, there's a repeat of the same event there. Sorry, what we're really interested in, which is the low adhesion value. So we call it mu. That's the conventional letter that's given, but ultimately the low adhesion value is what is the parameter that gives us a total, absolute, objective view of what's happening between the rail and the wheel. And that's what we're interested in, and ultimately then what we would feed into models to help inform mitigation, driver behaviour, but also aid the industry's understanding of the issue, such that we can develop technologies and solutions accordingly. So that's what we've done at Chiltern with KBRS. What else is available? So I hinted at vegetation monitoring. So Cordell Group is one example supplier that have presented to Adhesion Research Group that could form a key part of the expert trade, have a LiDAR artificial intelligence-based model that is able to intelligently anticipate vegetation buildup. So it takes historic scans of, again, to a very high degree of resolution, I believe to the nearest 10 centimeters, of the surrounding area of the infrastructure. So anything up to, I think, about 30 or 40 meters, I remember hearing, either side of the track, and is able to then build up through layers and intelligent monitoring capability, prediction of how that vegetation will look further down the line. And ultimately that then gives us an idea of when we may need to do something about it. And it's simply subject to the camera box and some intelligent monitoring capability on the front of the train. And it just so happens that the engineering safety case has actually been completed on Class 165s, because of course a GWR unit 165104 is fitted with this technology. So that presents an excellent opportunity to fit the same Chiltern unit that's been fitted with the in-service adhesion monitoring capability with this technology. There's also one big circle, which is able to monitor the railhead and generally the track condition looking downwards. They also have other capabilities, but for the purposes of adhesion, we're interested in high resolution photographs that are geo-mapped that can then be correlated against where low adhesion activity may have occurred. And then by piecing all these bits of the jigsaw together, we can ultimately produce a heat map that is able to tell us exactly where low adhesions occurred, to what severity, and what may have caused it. And then finally, we've got the data analysis, validation, and prediction output model that was able to bring everything together, subject to further validation, which is optional, but there's the capability of fitting accelerometers or additional measuring equipment in the cab. So this is a lot less intrusive to validate the data sources that I've just mentioned. And again, they come with their own software processing capability, but ultimately, I think if we do finally go ahead with this expert train concept, we'll probably end up picking and choosing various offerings from each supplier. So that brings us on neatly to Professor Roger Lewis, someone I've worked with very closely for a long time, very active in this work stream, who will tell us a little bit more about the academic side and how we've been collaborating.
Yeah,
Pointer of the screen.
there's a pointer on the. Yeah.
Okay, thank you very much, Louis. Yes, so I'm going to go back a little bit to look more at some of the fundamentals behind the whole problem of low adhesion, but also to show how we're moving our understanding out of the lab into the field, so it has some use for the industry. Won't dwell on that. So a little bit about our wheel rail interface research. I've been working in this area probably now for 20 years. Most of what I do is friction management, and at the moment probably focusing most on low adhesion, but we also cover all the other issues, some of which are interlinked with friction in the contact. So most of the other work's really about wear and rolling contact fatigue, and I guess rail grinding at the moment. So a lot of stuff going on at Sheffield where I work. Because we've been going for so long, we've been lucky to be able to build up quite an array of test equipment, which allows us to work right at the small scale. And I'll show some examples of some of the work we've done on just a twin disc machine. So it's essentially a disc of wheel material, disc of rail material, rotated under load against each other. We can accurately get representative contact pressures and slip values. Obviously quite a simplified contact, but it's easy to control and it's easy to take quite nice measurements of what's going on. And then we can scale up from there. The high pressure torsion rig, this is a way of getting a contact that's more of a representative size at the right contact pressure, but still with a really controlled test. And we've used that quite a bit recently in leaf layer work and in testing sand particles, different sand particles. We have a full scale rig. This is the old British Rail Research one, so quite old now, but still running well. So it's a linear rig, so we're pulling a length of rail under the wheel, so about 43 wheel, again under realistic loads and slips. And now we can go right up to field testing. So we actually own our own trains now at Schmandt. I'll come back to why later on. So the Wensleydale Railway up at Leeming Bar, where we can use the track. We've got a track circuit set up there for some work, which I'm going to talk about here as well. So it's really important for us to be able to test in the field. Lab tests are fine, but generally we find the industry a little bit suspicious of them. You know, these tiny little contacts testing, are the results transferable to the field? So a lot of what we do is working on how we transfer those small scale results into full scale outcomes. But at the same time, it is really important we can do full scale tests in the lab, but also get out in the field where obviously the condition, the environment are very different to our lab based, which creates lots of problems of controlling the tests. So lots of times when we go out to do leaf layer tests, we have to abandon because it's pouring with rain. More recently, we've had problems with snow and ice messing up the tests, but real conditions are important. So this is a bit of the Wensleydale track. You can see some leaf material there. We can roll vehicles over to create leaf layers. You can see some examples of this. We get a nice flat leaf layer there. We've got quite a nice array of equipment now for doing measurements on the field. So not just tribometers that allow us to put a machine on the track to measure the friction that surface is giving, but we've also got portable roughness measuring devices, laser scanners. This is more useful for the wear testing that we do. Important though for the friction side, and particularly low adhesion, we can measure the chemistry of the track in the field. Typically, people will go out and swab to understand what material there is on the railhead, but of course that takes quite a long time to get the results, and of course they may have changed by the time you get the swabs to the lab. So we've got handheld devices. We can simply go and point at the track and get quite detailed analysis of the elements that are there. Particularly useful when we're looking for leaf layer, and particularly useful in relation to something else I'll talk about later, and that's kind of non-visible contamination, which seems to be something that's coming to the fore at the moment in the adhesion research world. So I've worked on low adhesion through a strategic partnership we have with the Rail Safety and Standards Board. So I've been really lucky to work with them, and that's how I've connected with people like Rob and Louis to get the stakeholder involvement that we need to do our work. But like I said, we start at the very fundamental end, looking at very intricate analysis of chemistry and friction in the contact. And we built up through full-scale testing and other measurements to develop not just some solutions to the problem, but also some models that can be used to predict what's going to happen. So Louis mentioned one of them, but we also have friction prediction models as well, which I'll say a little bit about. So the causes of low adhesion or friction. I'm a tribologist, really, so it pains me to use the word adhesion to describe friction. Adhesion is what happens when things are sticking together. I understand why the word's used, though, but when I go back to the real world of tribology, I have to not use it, so I get criticised. But I like to show this map. It kind of pulls together all the different friction regimes within the wheel-rail interface and the products that we might use to move between them, depending on what's going on. This is one of the fascinating aspects of tribology, is that sometimes you have low friction and you really want it high, and sometimes you have high friction and you need to make it low. Where you want it high, you can't possibly have it low sometimes. So that's particularly the case of the wheel-rail interface. So this is the regime we don't want to be in, this one below 0.05. So we do in our group, we do a lot of work on lubricants that go in engines, car engines. Most of them, fully formulated car engine lubricants, will not give friction below about 0.06, but leaves will. So people have spent decades developing these fancy lubricants, but leaves are better. Sure, there's a potential product in there somewhere. One of the problems with leaves is the corrosion that they cause, so we can't have that happening. But yeah, so a bit of context around what we're looking at here, and obviously we have various mitigations that try and pull us away from that low level. Probably we don't need to get right up here though to have the right conditions. As long as we can get up to here somewhere, we're probably going to be okay. Although that does vary from train to train. So with the leaves, I thought I'd go right back to some of the very fundamental work we did on our twin disc machine, looking at various bits of a leaf or the chemicals in the leaf and how they affect friction. So we did some work on tannins. So these are the kinds of things you'll find in your cup of tea. So all leaves have got tannins in them. We did some work where we created essentially a leaf tea. So we had a beaker and we put some water in, a bit of rail steel, because the oxides that are generated from the steel are important in this whole process, and then some leaf material. So that leaf tea has tannins in. So if you look here, this is the friction result with just water. So we're up at a value that's probably about okay. With the leaf tea, though, we've dropped down to 0.05. If we treat our leaf tea with a chemical that suppresses tannins, though, it increases the friction back, well, in fact, higher, to a level higher than the water alone. So immediately we can see tannins in leaves make a difference. I'd like to say it was simply a case of us dealing with the tannins. There are lots of other bits of leaf that also cause low friction. Leaves on their own on the railhead will cause a slipping problem. So it isn't just about the chemistry of a leaf, it's about the physical material that makes up the leaf as well. But this is really interesting. It can start to give us an idea of how we might optimize some of the chemical treatments that we look at for dealing with the low friction. Bit on this. So this is work we did with the HPT testing. So that's the next one in the line of that scale diagram I showed up. So this is a flat on flat contact now. We press down at realistic contact pressures and we just twist specimens. This could allow us to develop a whole creep curve in one test. So that's the friction slip relationship. Or it just gives us a cycle by cycle analysis of friction, which is really useful. In a twin disc test, the discs are running at 400 RPM. We can't see what's happening cycle by cycle, but here we can look essentially and see what's happening wheel pass by wheel pass in terms of the development of a leaf layer. So we've got at this left-hand side, we've got leaf material piled up, and then we build up cycle by cycle. So the leaf layer thickness is reducing. The friction varies, but it's all around. So that's, sorry, it's quite small on here and a bit blurry, but that's about 0.09. So most of the friction is quite low. And we've looked at instances of adding more leaf material during the test, because obviously it's not as straightforward as the leaves being there and then we roll over them and it's all good. There'll be more leaves coming down. We use this approach as well for testing mitigation. This is a test we did on Alleviate, which is traction gel. So the green line is the leaf-only friction, which is hovering around 0.05. If we add Alleviate, these first cycles are just to generate the layer. We add the Alleviate there, immediately friction levels are coming up to about 0.2. So this is a really nice test we can use to generate leaf layers, look at what happens cycle by cycle, which we can't do in the twin disc test, but also to test different mitigations. So we've got tests lined up to look at other traction gels, but also some of the chemical products. I don't want to get into those at the moment, so I'm going to leave it there. Probably know what I mean. Yeah, so one of the problems I think with the mitigations at the moment is that there isn't enough data showing how they all perform. So we're focusing a lot on using these approaches to get more data on performance of some of the products. We have moved out into the field. Louis showed a few images from the work that Tom Butcher carried out during his PhD, which was sponsored by RSSB. So he did a lot of work trying to generate leaf layers in the field. Initially, his work was looking at different leaf types. So each leaf has a slightly different chemistry. Does that mean that some leaves are worse than others in terms of friction? Well, while they are all different, you can see here these are maybe 5 or 6 different leaf types. They all give low friction. So all leaves, if they end up as a leaf layer on the railhead, will cause low friction. Tom decided to go back from that point where we're on the railhead, though, to look at how the different leaf types get onto the railhead, and are there some differences there? So he looked at leaf fall and leaf mobility around the track, and in that case, there are some big differences in how the leaves behave, and certain leaf types are certainly far more prone to get drawn into the wheel rail interface and create leaf layers. So bigger leaves being worse, we think. Of course, if it pours with rain and they're all soggy, then there's no problem. So heavy rain in autumn is great. It also tends to wash material off the railhead as well. Obviously, going outside gives us the right environment to test in, and we've got varying humidity and temperature, but we can't control any of it, and it's a bit of a nightmare, to be honest. So we have recently done some work. This was part of a project we did with York University to look at how enzymes may affect leaf layers on the railhead. But as part of that, we created some leaf layers in our full scale rig and then took them into a big climate chamber where we can control the humidity and temperature and the moisture levels. And we started to get some really nice relationships coming out on how the humidity or separately added moisture varies the friction in the wheel rail interface. There's loads I could talk about there, but I don't want to dwell on that too much. But recently as well, we've got hold of the spinny rail rig from Birmingham University. Some of you may be familiar with. So it's 50 mile an hour spinning rail that we can also put in the climate chamber. So once that's set up, we'll be doing some more fun experiments. I'll be quite a long way away because it goes very fast, and if anything goes wrong, you don't want to be too near it. Most of the talk today is going to be about leaves. I wanted to say something quickly about wet rail because wet rail can happen at any point during the year. And of course, that's where we've got small amounts of moisture mixing with a little bit of oxide on the rail to form a slippery paste. So we did some work with RSSB over a number of projects essentially trying to reproduce this in the lab. People were aware it was happening in the real world, but what were the conditions that caused it to happen? So this data is from a full-scale rig in the Czech Republic that we used. So this work predated the Harold rig in Huddersfield, which we used for some later work. So this lab is located right next to the Semtex factory, which I'm quite interested in. Younger people may not remember what Semtex is, but you can see here we were putting different amounts of water into the interface. So this blue line is essentially the dry response. So this essentially is a friction coefficient against the slip value of the contact. So we're going up to very high slip values, but anyway, dry value is quite high. But then the next highest value is the highest amount of water we applied, which intuitively is not what you think will happen. You think lots of water is going to give you much lower friction. But see, the 25 microliters per second actually is the one that gives us all the low friction problems. And that's because that small amount is enough to generate with a bit of oxide a slippy paste. And the reason that the small amount works better is because there's a very small envelope of proportions of solid to liquid that cause the low friction. So on this graph, you can see that the solid oxide fraction, so it goes from 0.6 up to 1. And this is the point where the low friction occurs. So you can see it's somewhere between maybe 0.9 and 0.98. If you go back a bit, you have too much liquid. So it's enough to clean out the oxide and there's no problem. And you go the other way, then it just becomes dry and you essentially get dry friction. But that is the point where we will get low friction due to wet rail. Now, how that actually happens in the real world and how that causes a long train slide is still something we're working on understanding. But we've recreated the problem in the lab, which is interesting. Now, sometimes when you have oxide and water mixtures, you can't actually see them on the railhead. And we noticed this when we were doing the wet rail work. More recently, it's become noticeable in some of our leaf testing as well. Sometimes when we've removed the visible leaf material from the railhead, we still have low friction. And this is something that the adhesion research group has started to get some interest in now. So we did some tests recently on our full scale rig. So we have a kind of standard approach for generating a leaf layer in the rig. So we put some leaf mulch down, we roll over. So the way the rig works doesn't roll in both directions. At the end of one cycle, the wheel's lifted and the rails return to its original position, and then we roll over again. Again, quite useful. We can do cycle by cycle tests, and we can look at what's going on the wheel surface and the rail surface. If we want to then mimic another wheel coming along and rolling over it, we'll clean the material that accumulates on the wheel off and then roll over. In this case, we didn't do that, but I should point out a lot of leaf material does end up on the wheel. So we focus a lot on leaf layers on the rail. There are problems with leaf layers on wheels as well. Not so easy to study, because if you're looking at a particular length of track, the leaf layer stays where it is on the track, whereas the vehicle disappears off into the distance, and you don't know what's happened. Something we can remedy through testing on our rig. So what we did was we created a layer, and we have friction data for the cycles with the leaf layer there. And then after a certain point, we decide, right, we'll remove it. Not scrub it, just literally peel away the dark leaf material, leaving behind what potentially might be any non-visible contamination. So here you can see that in real world photos. So we've got our leaf layer building up. See a nice black leaf layer there, and then we remove it. So now we've gone back to a clean rail, well, visibly clean rail and a visibly clean wheel. This lot's quite complicated. This is the data that we got from the point where we removed the leaf layer. We wetted the rail a little bit. Moisture is really important in the low adhesion problem. Without water, not a problem. If you have small amounts of water on a leaf layer or with oxide, then you have a problem. So each of these kind of spikes is a cycle. So remember, we only put the leaf layer over half of the running cycle. So the first part is still dry and clean, and that's giving an average of 0.2. But the second part, where the leaf layer was slightly wetted, is giving an average friction level after the visible material's gone over somewhere about 0.07. So we ran 60 cycles. The friction goes up as it dries out, but then when we re-wet, it goes back down again. And we did this over many cycles, and as we kept re-wetting it, the friction dropped again. So we can't see anything on the surfaces, but we're getting this persistent low friction. So whatever's there is not removed by the wheels, quite high slip values we were using. So really interesting, but it kind of makes the problem even more complicated. Most low adhesion tools, the ones that we work on and Lou is talking about, are using images of the railhead to determine whether there's contaminant there, to decide whether there's a low adhesion risk. Well, of course, if what do you do then if it's an invisible contaminant? There are ways to look at that. But I think Louis mentioned the focus on sanding research has been massive, both in our research and other people's. This is some work we did on the HPT machine, so we can grow leaf layers and then put sand particles in and see. That's a leaf friction level. That's what happens when we have sand particles in. We've tested probably 10 to 15 different sand particles from all over the world. Everybody uses slightly different ones, different size, slightly different material. They all seem to work okay. There are trends you see with regards to materials and size, but generally sand works. We've looked at this is just an example of different hardness values for the particles. They're all working pretty well. Perhaps not so well at the softer end, but you're still getting to a level of traction that's useful. We've helped some other people develop models that allow you to simulate sand being applied to the wheel rail interface. So we've done crushing tests on individual particles and look carefully at how they indent the surface, how they spread as they pass through the wheel rail interface, and so on. So, and we've done testing in our full scale rig as well, both on traction gels and we can put a whole sander on and do tests. So most of that work's been focused on looking at how much of the sand actually goes into the wheel rail interface, because with a rubber hose that's flapping about a bit, not a great deal is what I would say. There are better devices available now for ensuring more gets in. Something that's followed on from that is some more work with RSSB, looking at conductive particles. So this is to try and overcome the problems that may exist with isolation of the wheel from the rail that's due to sand, which is very unusual, but it does happen every now and again. And obviously the amount of sand that can be applied is limited because of that. So if you had a conductive particle, the thought is you could eliminate any possible track circuit problems, but also you could apply more sand, because if it's not going to be a problem isolating the wheel from the rail, then we can put more in. So we did some work in the lab initially, again with the HPT machine, measuring the resistance across the circuit. So you can see here, this is normal sand, so we're getting a problem with the resistance there. With the new particles that we're testing, or the conductive, no problem. So we've tested a few different suppliers' products. They will have slightly different concepts, but they will work with, of course, it's important that they work on the traction enhancement side as well. This is just the data for the track circuit, but they all increase friction in the way that current sand does. Again, though, we needed to get out of the lab, so we went up to Wensleydale. We have a track circuit set up there now, so we were creating leaf layers, and we were applying these new particles from the sander on our Class 142 train. And we're able to show again the particles work. They can be applied okay in the way they're meant to be. We did some very simple brake tests, but we could only run at 10 miles an hour on this stretch, and that's not going to build the confidence we need to know whether the particles will work okay on trains on the network. So we were very lucky to piggyback on the back of some trials going on at Tuxford with
South Western Railway 158s, 159s, when you hit them with single variable rate.
yes.
Numbers.
Didn't write that down. Ross remembers all this stuff. It's great. So we were able to do with so we had paper tape laid down to simulate a leaf layer, and we were braking it from 50 miles an hour, so full brake testing, which was really quite a unique opportunity. So we were lucky there. You can see here the stopping distances from 50 miles an hour. So the blue line is the current sand. This orange line is one of the new conductive products. So stopping slightly shorter. I mean, some other issues around the application that may have caused that, but certainly very comparable with current products. So this has provided us with enough data to get people to agree to us putting these products on trains on the network. Just need to find out a way to actually make this happen, but that'll be really exciting. Somebody needs to work out how to make the particles more cheaply. Traction gels, this always seems to be quite a contentious issue. I remember National Autumn Review where people were arguing a lot about whether these actually worked. Well, they do work. We've confirmed that in the lab and in the field. You might get a little drop in friction when you first roll over the gel, but once the gel's been squeezed out, the particles left do enhance friction, regardless of whether there's a leaf layer there. So if they're just out on the bare steel with no contamination, they do still also work. So we did this field testing of the products at Long Marston. So this was with an even older train, 115. So we created leaf layers and then braked on them. Yeah, this is very blurry.
Yeah, unfortunately.
Yeah. Yeah, so these points here, the dark points there, leaf layer with traction gel. The lower pink dots are more likely to be the leaf layer on the top. So you can see it is making a difference, and we're getting a longer braking distance. The other thing we're able to see is how the product or abrading help to abrade the leaf layer as well. So they definitely work. How many train passes one puddle works for is another matter, but then you can keep pumping it out more frequently if you want to. So I'm not going to go into these slides too much because Rob's going to say a bit about this later. We've been very lucky to work with Northern over quite a number of years now on a new railhead cleaning technology that works with dry ice. And the culmination of that is a system that can fit under a passenger train to apply the particles onto the railhead. So this will allow more frequent cleaning during the day, which should help stop contamination layers building up, so that you don't need that really powerful clean that you get from the railhead treatment train. And we've iterated through road-to-rail vehicles, the Nexus Tyne and Weir railhead treatment train, which is kind of a very scaled-down version of the network rails. And then we borrowed a few northern trains to put the system in the saloon area to clean. But now the whole reason we had to buy our own trains was we can't make changes to box trains. We get upset about holes being drilled and bits being cut off and stuff. So we can do what the hell we like with our own trains then, which is good. So these are approved to go on the network. One of these was on the East Coast Main Line earlier in the year. Hopefully you were all over social media and watched it go through. Was it Durham Station?
Yeah,
75 miles an hour.
Goodness me, on the pacer.
Yeah, well, I was horrified when I imagined it might be shaking itself to bits. And if we get stuck on the East Coast Main Line, I might be in a bit of trouble. I've not read the paperwork properly to understand how well I'm insured. So I'm not going to go through any of this except to show this video, which shows the system working. Hopefully, I've not checked this, but normally has funky music playing at the moment. No. So yeah,
Oh,
there you go. So this was shots of the Wensleydale Railway. This is the nozzle. You can see it blasting out and cleaning all the muck off the track as it goes out there. We weren't able to clean leaf layers in the shop. It's just it's exactly how it works in the railway. Bob will explain more about this. So this whole system fits underneath the Class 142, and it's self-powered because there's no utilities for us to tap into on the 142. So we have a compressor for the air and everything all underneath the train. So you can look forward to what Rob said. Louis mentioned some of our work on what we call, low adhesion forecasting or friction prediction. We've done a lot of work jointly with University of Huddersfield on their Harold rig, generating leaf layers and measuring friction values. You can see here, we actually got below 0.02. You can see some of the black leaf layers we created. So we use the output of that to parameterize a model. So now we can generate creep curves, so that friction slip relationship. And how it varies with different amounts of leaf in different conditions. So this model is now integrated into the Labrador train braking model. So we can use that to look at how leaf layers and low adhesion conditions influence train braking. I guess there's a number of different classes of train we can model in that now. The other way this could be used is to put these into multi-body dynamic simulations, so we can see generally how overall train performance is affected by leaf layers. We have similar curves now for sand. These have come from the HPT test. So we can take the scaled down HPT data and use what we call a creep force model to parameterize. We can parameterize the creep force model for the different types of sand under different conditions. And with that, we can do full scale predictions, which again, we can generate curves that can feed into train performance models. Here we've compared our model output with data from the Advanced Lab train, which is a train that runs in Germany, which is fully instrumented. But they did a big series of leaf layer tests and sanding tests with this train to generate this kind of data, looking at that they could look at friction levels between axles as well, which was quite nice. So the leaf layer, our model's saying about 0.04 for the full scale, and they were doing measurements between 0.04 and 0.1. And then with sand, we've got about 0.14. They're somewhere between 0.02 and 0.16. And the 0.02 would be towards the back end where the sand has become less effective. So, some useful modeling. This is some more work we've done with our SSB. So we've created a very simple camera box system that we can use now for gathering data for estimating friction in real time. I guess it's a slight variant on some of the other tools that just use images and look for contamination. Here we're looking at forward-facing images, railhead images, and we've got temperature and humidity measurements. So the humidity is actually the most important measurement for us determining how damp everything is. So during COVID, it was great, not for many things, but it was great because we could get out on track. It's easier to get out on track than it was to go into our own labs. Normally it's the other way around. So we gathered lots of measurements we could use to train a model. Now, obviously, that's just the model. We had to have some way to kind of implement it. So we developed this very simple camera box system, a few £100, hang it on the lamp bracket. As long as the lamp bracket's over the railhead, it's good. So we get forward-facing images, we get railhead images, and then we gather the temperature and humidity data. We've run this now on the actual network, but also up and down Wensleydale and over leaf layers that we created. So you can see here these dips in the friction value have come from 3 meter stretches of leaf layers. So it's pretty high resolution. So this is data from gathered all the way along the track. So I think slightly more useful than just having the image. And it could be something we use to deal with the whole non-visible side because of the temperature and humidity measurements that we're gathering. So we're hopefully going to license this to a small company in Sheffield who wants to try and take this forward. But at the moment, we're working with TfL to put this on one of their rat trains, the ones that put sandite out. So that involves now, so we can't hang that on the front of the train. It's got to be more integrated to get through their approvals processes. So we've improved the imaging side of it as well, which is good. Again, Louis did mention this. This is the project we did with him, SSB. So we've created a low adhesion risk model that takes very simple inputs that you can gather, well, if you really want to, from Google. So these are some Google images of various station sites. So we started off looking at station by station. So Louis had data on the wheel slips, station by station. So we use half the data to tune the model. So the inputs are all largely around trees. What type of tree? How close are they to the track? How dense are they? But other factors like are you going through a cutting, so on. And so we tune the model with half the data and then use the other half to validate it. That looked quite good. Then we used images from AIVR to look at some other routes because obviously we get images then all the way along the route, not just station by station. And that's been really successful. I'm not going to go into this too much, but there is
the key thing is we've got the framework here to be able to now test the model with much better inputs.
Yeah.
So the model is now as good as its inputs. The model architecture is there. Yeah. Now with the newer low adhesion monitoring data and AIVR and all the other work streams that are developing, hopefully within the next year or two we'll be able to produce something that we can roll out nationally.
I want to know more. There are 2 papers about to appear in the PWI journal. First one's coming out in January. I'm not sure about the second one. Guess it'll be the next issue. Yeah, so look out for those and you can read more about that. Yes, so that's me done. I'm going to hand over to Rob to talk more about the kind of innovation side. The train operator's perspective.
Thanks, Roger. So yeah, good evening. I'm Rob Cummings. I'm a seasonal performance improvement manager at Northern. It's a role I've now been doing for 10.5 years. I've just completed my 11th autumn. I came across from Network Rail in 2015 because they wanted somebody to try and work a lot closer with Network Rail on low adhesion. So yeah, it was quite fortunate that I just happened to be around at the time. I'd been doing vegetation management and been involved with the RHTTs and the MPVs at Network Rail, so it was quite a natural progression for me. So autumn, the risk of the number of safety incidents, key priority, signals past the danger. Good news was we didn't have any last year, although we've had 8 since 2008. Station overruns, we had 17 this autumn. Which was about par with 2024. It was about a third lower than 2023. 2023 was quite a bad year. When you think we operate 2,500 services a day, if you said on average they stop 10 stations each, that's 25,000 station stops every day 70 odd days in autumn. So to have 17 is still pretty good. Even though we'd obviously like it to be a lot less. And then, as Roger mentioned, we can get wrong side track circuit failures. This is where the leaf contamination prevents the flow of electrical current between the wheel and the rail that causes track. Is how a track circuit works. So if you insulate the wheel from the rail with the leaf contamination, we basically get a failure of the track circuit. Obviously, we've also got delays. Drivers are encouraged to drive more cautiously, more professionally. So put the brake in earlier, use a lower brake step. So if you know what provokes a slide often is moving into a higher brake step. It's funny, every autumn's different. We showed an improvement this year, but I think part of that is by virtue of the fact that it's funny as well, but Northern being kind of northwest and North York, Yorkshire and the northeast. Last year, the Yorkshire and northeast was really poor, and the northwest did really well. This year it flipped, and because it was so different. You know, this is right, so arbitrary. Well, obviously, we want to try and get the delays down ultimately. And then wheel flats, it's not as big an issue now. When we had the Pacers, it's a good job Roger's running them now and not us. They were horrendous. We about 2/3 of the flats we get every season were with Pacers. It's basically where the Pacers slide. Well, any train can slide, and it creates a flat on the wheel. If that flat goes beyond 60 mil, it has to come out of service and go on a wheel lathe to have the flat removed. That obviously wipes thousands of miles off the life of the wheel as well. But it also, you know, obviously you've got trains out of service. We don't have a lathe in the northeast. So if we got a flat on the Pacer in Newcastle, we'd have to move it at 25 miles an hour down the East Coast main line to Neville Hill in Leeds, which was always a challenge. Obviously, only ever happened overnight. But yeah, 2018, 308 units stopped through the season. Since we got rid of the Pacers, we've bought 101 new CAF trains that have got a wheel slide protection system. We've retrofitted wheel slide protection system to the 150s, the 155s, and the 156s. You know, we're now getting less than 20 a season, so it has improved dramatically. It's one of the positives over the last few years. Obviously, signals passed at danger. We've had the 2 incidents, Salisbury in 2021 and 2024. That just shows how serious it can be. We had a very near miss in Darlington in 2019, which again just goes to show how unpredictable this can be, because Darlington is a big wide open area with not much vegetation. We think there was a GNER train that had braked into Darlington station with contamination on the wheels. As Roger mentioned, it can transfer between the two. In this instance, the contamination transferred onto the rail. Pacer comes in off the junction from the Middlesbrough direction, picks up the contamination and slid into the station. Fortunately, it was the same platform where the GNER train was, but he'd been given the signal to go. So they kind of kissed as they were both going in the same direction. So we didn't have the head-on collision that happened here, but it just shows how serious it can be. So the problem statement, basically, as you're going along, you're creating these circular air currents, and they suck up the leaves and almost in one motion pass them under the wheel. Then you get that crushes the leaf, and you get the change in the chemistry due to the high pressure and the heat, and it creates this Teflon-like coating. As Roger mentioned, if you have a little moisture, dew or light rain, that can cause a low adhesion, and that's when we have the problems. It is amazing when you have heavy rain, what difference it can make. You know, the problem almost becomes non-existent, and we'll come in a bit to a trial we've been doing to try and improve things by using water. Trains running with steel wheels on a steel rail, so it's a low friction system. Obviously, 10 months of the year, that's an advantage in terms of energy consumption and efficiency, but it's just an Achilles heel when we've got a bit of low adhesion around in the autumn. And again, it's not every day. It depends on the conditions. As Louis mentioned, that the contact point's about the size of a 5p piece. All traction and braking forces are transmitted through this small area. So this is the problem we're up against. And it's interesting, you know, down the years, we've started to work that interface so much harder in terms of the braking and acceleration. It's quite interesting when you go around other countries. I've been riding around the regional trains in France for 3 years, and it seems to be a lot more gentle. We brake into the station. You have quite 2 minutes dwell time, and then you gently ease out. And whereas we're brakes, doors open, everybody on off, brake, doors shut again, off we go. And this is why we seem to have a particular problem. So Network Rail use these 4 levels to describe contamination. On the top right, level 0 is a nice clean dry rail. You're starting to see splodges of contamination on level 1. Level 2 is a bit moist, you still see some silver coming through, and then level 3 is a really badly contaminated rail. It's not a new problem. There's actually a Railway magazine article from 1836. It was the Manchester and Liverpool Railway were struggling to get up Whiston Plain. And that's a location that still exists on the Northern Network, but obviously we race up it now with electric trains. But they actually had 2 guys sat on the buffer beam with a steam locomotive throwing sand from buckets onto the railhead. And it just makes me laugh. It finished off by saying a remedy, however, I think will not be difficult to find. Almost 200 years later, we're still battling with that conundrum. So what else has changed? Well, the first generation of locomotive haul trains of multiple units were replaced with lightweight DMUs and EMUs in the 70s and 80s. The Pacers and the Sprinters weren't fitted with sanding equipment originally. It wasn't deemed to be an issue. They were all retrofitted about 2010 when we had a really poor autumn. Modern units are fitted with disc brakes, so they work out onto the inside rim of the wheel, whereas tread brakes are working onto the outside of the wheel, and they have a cleaning effect. So it's interesting, on the 158 fleets that have disc brakes, we've also got what they call scrubber blocks, which effectively are a tread brake in that when the disc brake activates, that then works against the outside face of the wheel to clean it. As I mentioned, we've got the higher adhesion demands for acceleration braking, and we've also got more backline side vegetation. First identified as a problem by BR in the early 80s. This paper was produced by BR Research. There was problems on the Chiltern line, especially before Lewis time. And also there was Southwestern, I forget the unit type now, but there was quite a famous picture of one that overran. Was it West By Fleet and finished up hanging out over the road?
So that was a fun fact on Chiltern. 165004 was chosen for production reasons, but also because it was the Brell experimental WSP unit back in the early 90s. So there's a bit of a tradition about Unit 165004. The sponsors amongst you.
What this also recommended was a programme of tree clearance, including removal and burning of debris. I'd love to be able to do that now. We've not been allowed to do that for a number of years. Also suggested a sprinkler system in the forefoot at high-risk locations, spraying water onto the railhead to replicate heavy rainfall. Well, we've taken that a step further. That proved to be impractical, but we'll come to a slide in a bit where we've reversed that to try and create or solve the problem. So vegetation, how have we got here? Well, the end of steam traction removed the risk of line-side fires. Steam locomotives were like mobile arsonists. It was interesting, in April last year, there was if you remember, it was a very dry spring, and they ran a steam charter up the Cumbrian coast, and it caused a huge amount of line-side fires and burnt through signalling equipment and closed the line for a couple of days. So that gives you an idea of how bad it could have been. Obviously, we had the reductions in maintenance budgets, we had changes in maintenance practices. We couldn't burn the vegetation. You had to cut it, chip it, or remove the logs from site. We've got legislation, the 1983 Wildlife and Countryside Act, so you can't disturb nests between it's 1st of April and the end of August. You can still get around it. We use ecologists to carry out surveys every day, and they barrier off if they find any evidence of a tree that's got a nest or even a ground nest, they'll barrier off the area and you have to leave that. Obviously, the Clean Air Act prevents burning vegetation, and you get quite a lot of objections from people that bought houses next to the railway and don't want to see the trains. We were doing some work on the Harrogate line a few years ago, in fact, just before the Salisbury accident. And Network Rail had put the work off all through the spring and summer and finally got round to doing it in the autumn, which is the worst time to be doing vegetation. And there was still, despite all of the work they've done with line-side neighbours, there's still a lot of social media commentary about how we're destroying the environment and stuff. And then Salisbury happened, and it was quite interesting to see the backlash against these people saying this is why we need to do it. But yeah, it's, you know, when I first started with Railtrack, we used to go out and just clear vegetation overnight, field the complaints on Monday, knowing we'd finished in that area and moving on to disturb somebody else the following weekend. Can't do that now. You have to send newsletters out and tell people what you're doing. This is the old Network Rail vegetation standard. It's up to 60 miles an hour. Basically, oh, I'll use the pointer, can't I? Is that it? Yes. So you clear through. You could clear 3 meters from the nearest running edge, and then above 60 miles an hour, you could clear. It was 5 meters. That's now changed because it didn't eliminate the problem of trees falling across the tracks. You know, it's not just an autumn issue. We have storms, trees blowing onto tracks and overheads. We also get signals obscured in the summer. So this standard, you've basically got the immediate action area, which is the 3 meters either side of the running edge. You then take a 45-degree line from that point to the boundary, and that's the action area. And that the idea of that is to prevent stuff falling onto the track. This was brought in 2018 because it's such a massive job to kind of get the network up to this standard. They've got a derogation until 2033 to actually complete it. I think that's now slipped a couple of years. But that once this is done, this is the ideal scenario for us. It's quite interesting photographs from the RAIB report from Salisbury. So the 2 pictures at the top was historical around the tunnel, and then you look at it, you can hardly see it around the time of the Salisbury accident. We've also got, this is me and my dad in 1966. This is Cheadle Hulme, just south of Stockport on the West Coast Main Line. You know, really well maintained line side. You see, I was destined to do this work. You'll see the thought bubble. Look at well maintained bit of line side, and that's what it looked like in 2018. You can barely see. Well, you see half of 2 Voyager coaches going over the viaduct. So, in terms of mitigations, Network introduced the MPVs in the early 2000s. They are looking to replace them at the end of this control period or early into the following one because they're starting to show their age now. So it's a fixed consist train. It basically jets the railhead at 1600 bar, which actually, if it's stationary, is sufficient to cut through the rail. But yeah, it's had a cut off below 10 mile an hour. And it's also the rail. Oops, wrong button. The rail treatment trains. These are locomotive hauled. Same jetting equipment, jet at 1600 bar. Well, you could add tanks and get a much bigger range on these than you can with the MPVs. Disadvantages: it's a dedicated train. It's very expensive. £65 million nationally to do this. I mean, you know, on most of our network, we're getting a circuit. Well, there's 6 in the northwest and 4 in the northeast. Every day, 6 days a week. Some run 7 days a week. Some south of the Thames run twice a day, 7 days a week. So it's a huge exercise every autumn. We lose treatment due to clashes with engineering possessions because we often run them at night. We lose treatment due to equipment failures. We're running very high pressure jetting equipment and it's prone to failure. Most routes only get treated once a day, 6 days a week. So as Roger mentioned, you know, as soon as you've cleaned it, the contamination is starting to build up, which is why can we treat lines several times a day with equipment fitted to passenger trains. Route restrictions, limited use of modern locos. We used to have a bridge at Barnsley that you can only get to class 20 underneath. That's now been demolished. That was demolished just ahead of COVID. So that problem went away, but now we've got the Wolds Coast that can only take class 37s, which are now well into the 60s. So I don't know what the long-term future of those are. And the MPVs are obsolete, as I've already mentioned. Traction gel applicators, Roger briefly touched on them. It's a bit of line-side equipment we usually have around stations. Train hits the treadle and it squeezes out some adhesion modifier, which is basically a sandy gel onto the railhead, and the train spreads it over a fairly limited area, but it's quite useful when you break into a station or trying to gain traction and accelerating out of it. And then we've also got the scrubber machines to manually scrub contamination off the rail. So northern mitigations, obviously, as I've mentioned, we've gone from the Pacers to the non-CAF fleet, although it's only a quarter of the current fleet. We are hoping to order some new trains for the early 2030s this spring, so we'll see what happens with that. I mentioned we've fitted wheel slide prevention systems now. There's 7 Class 155s in West Yorkshire that's basically too small a fleet to justify the design to fit them. So they're the only ones now that aren't fitted with a wheel slide prevention system. We can get data live from the CAF fleet through lead mine portal, so you can actually see where they're slipping in real time, which really helps us planning mitigations. We fitted double variable rate sanders to the Class 323 fleet. So this is basically, the name describes it, you've got a second sander, but it can also drop a higher rate of sand at higher speed, and then it slows down as the train slows. Water tractor system, spraying water onto the railhead to replicate heavy rainfall. And then we've also got the wheel lays. We've got an extra one now in Manchester, Liverpool and Leeds, but we still haven't solved the North East problem. We do a lot of work with drivers, so Cabs magazine communicating about safety, that has a special autumn edition every year. Encouraging drivers to drive to conditions, brake early at other time of years, observe the correct braking instructions. Different fleets have different braking instructions, so the electric trains, generally we say put it in step 2 straight away and let the WSP do its work. With the older diesel trains, you put it in step 1, which is a lighter braking, but again, we've got WSP on most of the fleets now anyway. Carry out regular running brake tests. This is just as you're going along, you're not actually planning to stop at the station. Just put the brake in and see if there's any WSP activity or any kind of slide, just to get a feel for what the conditions are. If you're in any doubt you're going to overrun a signal or a station, just put it in emergency. All newly qualified drivers have a face-to-face briefing prior to the start of autumn. And we're finally getting some new driver simulators. These have been a proposal we've actually had to move our training schools in Manchester and Leeds because the floors in them weren't strong enough for these. If you've seen the airline ones that sit on legs and move around, apparently they're very similar to that. So we had to have we had to move to somewhere with a stronger floor to accommodate them. Whiteboards, basically we have a whiteboard in every driver depot, and drivers are encouraged to, so if they encounter something when they're out and about, just to record it. It's to help other drivers who might see it. Also, we try and get this data and pass it on to Network Rail. This is basically if it's a bit slippy, but it's autumn. If it's like, oh bugger, that's a bit slippy, that's worse than I expected it to be. Drivers should actually stop and report it to the signaller. And then we'll get Network Rail, we'll get somebody to come out and inspect the rail and scrub it if need be. So looking at that, I think that's Barrow in Furness, looking at the locations. So this is reportable. The Network Rail produced this poster, Tiger, track is good, expected or reportable, which is when you need to get somebody in to look at it. Sander system, so sanders are now fitted on all UK trains. Deposit sand at 2 kilograms a minute. It's an open system. We've got no indication that the pipes are blocked. So Taladig, there's this interim report came out earlier last year that suggested that the pipes are blocked on that unit. So there's a lot of work now going in on how we can detect if sand's actually coming out of the sanders. We discovered we had quite a few incidents with the new CAF trains in 2023 and found we were dropping insufficient sand. There was a bleeder valve was blocked on them all, so we had to change all those. There was also oil leaking into them from the compressor, which we've now overcome. And yeah, and it cost £400,000 to put it straight before September 2024. So the innovation projects, Network Rail has an performance innovation fund that we've tapped into for Roger's project, the cryogenic railhead cleaning, also the water track and double variable rate sanders. So yeah, double variable rate sanders, you've got, that's where you traditionally have a sander. You leave your first 2 wheels free of sand to activate track circuits. So what double variable rate sanders is a second sander ahead of the 7th axle. and obviously the blue ones are for the different direction of travel, and they will drop between 2 and 4 kilograms, and that varies with the speed. It's quite interesting. What we're finding is that it's performing really well. We've not had a single. It's now been in for 2 seasons. Not a single station overrun on this fleet that's historically had issues. So it seems to be working, but we get to, well, as you'd expect, to double the amount of sand, which is quite interesting. And are we going to see things like wet beds going forward? It's fortunate the areas we use them have got pretty good track circuit systems, but the concern is if we do something similar on the Yorkshire side, where they've got a lot of low voltage DC track circuits, would that cause some wrong side track circuit failures? So that's quite a bit of working before we roll out any further fleets yet. But this is an RSSB trial that was done in 2016, 2017 with double variable rate sanders, and you can see, this is what the result you got compared with single fixed rate. It's so much better. So yeah, we've fitted all 323s. We've not had any safety line incidents. We carry out an evaluation process. What we're finding is it's taking a few seasons to build driver confidence. So we saw a little bit of a performance benefit last year, saw a little more this year. Maybe next year we'll almost be driving them like it's a normal day. South Western have fitted single variable rate sanders there, 158s and 159s. There's a big push in the industry to roll that out across all those fleets, just purely because they were involved with Salisbury and Saladig. So they're the priority for the industry. But it requires a business case, and it's currently very expensive and potentially over complex. Obviously, if you can fit it to a new fleet, it becomes so much easier. Water tracks. So this is basically a system that sprays water to replicate heavy rainfall when the train detects, or when we get wheel slide prevention activity. So we've been gradually trialling this since 2000, initially on 2 electric trains in the northwest. Last year we fitted an entire Class 170 fleet. We've got some promising results, but we also had some overruns. So we're looking at can we tweak the system to improve it. There's some findings we've made from last year. So that's what we're hoping to achieve for next year, get it back in service and working more effectively. And this is just some graphs showing the benefits that we showed from using water track. So the water track's not quite as good as heavy rain, but it's improved. It provides an improvement on poor adhesion. Obviously, water isn't going to cause the same kind of issues that sand does on the railhead. And then finally, cryogenic railhead cleaning. You've seen that slide before, and that one. Basically, I think it was 2017. I got 180,000 off Arriva, who had our franchise at the time, to fund Rogers guys to fit their kit to a manually propelled trolley and push it up and down a freight branch in Barnsley. It's evolved then through this RRV. I think, yeah, we then got it on the Nexus Tyne and Weir. Then we fitted it in the saloon of one of our units, ran some hoses out the window, and ran it in an overnight possession between Leeds and Wakefield in 2022, 21, I can't remember now. But obviously, where we want to get is to where we fit it under a passenger train and take out a lot of the cost. And also, you can clean a railhead several times a day. You've not got the problem of engineering clashes. It's such a win-win potential for the future. So this is a freight branch near Barnsley that it basically used to be a main line, so there's a lot of mining subsidence. It closed in the 80s, but there's a glass factory at the end of the branch, and there's 3 freight trains a week take sand in. But we use it it's like our low adhesion test track. It's really helpful. But we fitted a northern unit on that as well and trialled the railhead cleaning equipment. And then this is the 142s. It's quite interesting. I had a colleague who was I think he was treasurer of the Wensleydale Railway, and I happened to mention that we were looking, we might want to buy a train to do some further trials. Was it 8,000? You can buy a second-hand car for that, could you? So it was a real bargain. And we helped the Wensleydale because they just taken on, they've got loads, they've got pacers to spare. The irony was when they turned up when they were first donated by the rail leasing company. They all arrived with full fuel tanks, and they reckon the fuel was worth more than the Pacers. But the next step is to get it on the main line. We had hoped to get it on this autumn, but we didn't quite get all the main line certification sorted in time. It's quite frustrating. You know, we have this 8-week window, 8 to 10 week window every year, and you've got to be ready on the 1st of October, and sometimes it doesn't always happen. So the future, compliant line sides won't completely solve the problem. Got a lot of third-party trees, but it will provide a significant improvement. Also reduce the impact of storms and fallen trees and signals obscured by vegetation in the summer. Auto-agnostic trains fitted with DVRS, water track and the sensors that Louis mentioned. Still need railhead cleaning, or could it be delivered on service trains using the cryogenic process? And magnetic train brakes. We don't use these in the UK. Fitted to a lot of UK trams and on continental railways, very difficult to retrofit. But an opportunity for new train fleets, perhaps. And it's interesting that the RSSB did some research on that a few years ago and could see no reason, basically concluded no reason why we couldn't roll it out on the UK network. But when you ask the Network Rail engineers, there's still quite a bit of reticence about running a magnet on the top of a rail when you're trying to brake.
We're slowly making the case, though, aren't we?
Yeah, slowly
like
making
the
the case.
backbenchers. We'll just
So
we made the case.
rattled through it a bit, overrun slightly. But that's it. I've got any questions.
Excellent. Okay. So, if there's anyone in the room, if they could signal, excuse me, I don't know everyone's name, so I'll just have to point and sort of gesture to whoever is to speak. And if there's anyone at home wants to raise a question, please mark with your raised hand on the Teams, and I'll come to you and ask you to raise your question. We got any takers to start the ball rolling in the room? Malcolm.
Very interesting, and you can go back many years on these sort of things that what we had to do and the things that we've been put in practice. Can we just go back? We've never mentioned freight trains tonight at all. When we've got local haul trains, and of course with higher axle loads and so on, with different wheel sizes, different wheel profiles as well on the thing. We don't seem to have the problem with and so on with the freight trains. Is it a fact that and is the weight of the trains so on as against the very lightweight unit, passenger unit generally? Is it actual fact? And things like, say, the Class 800, which are considerably heavier, especially with the diesel units inside them, are they prone to the same sort of problems as, say, 156s or 1500 or something?
No, it's a different problem. It's still a problem.
At least we didn't have time to cover it.
We have issues with freight trains coming to a stand on gradients.
Yeah.
There's a particular freight flow in Lancashire, Castle Cement coming out of Clitheroe, and there's a bank, Worley Bank, but just ahead of Worley Bank, you've got the viaduct, Worley Viaduct, and there's a 20-mile-an-hour limit for the axle loads on that train. So it's going over the viaduct to 20. Then after clear the viaducts before they can open the throttle, and we've had numerous incidents down the years where the train struggled or stopped on the bank, and Network Rail have cleared vegetation and put a series of traction gel applicators in. The only way we managed to solve it in the end was to lower the amount of cement in each wagon, so you could have a lower RA and actually run over the viaducts at 30. And since they've done that, but that's eaten into the profitability of the brake flow. We also had along a similar area that there was a bitumen flow from Preston across to Lincolnshire somewhere, and that actually stopped at some point last autumn, and the very last train slipped to a stand on the Calder Valley line and caused quite a lot of disruption. But the other thing with freight trains is we had I don't know if you remember seeing it I can't remember when it was 2021 or 2022 Petrel Bridge derailment, and this was basically a wheel flap. And the train had, I think the wheel had actually, the flap was so bad, the wheel had locked up, and it got dragged all along the Settle Carlisle line, past half a dozen signal boxes where the signalman's supposed to be looking out for glowing wheels, got to Petrol Bridge Junction just outside Carlisle, derailed. Some of the cement wagon finished up in a B&Q car park, which might be some innovative way of delivery of materials, but it kind of blocked that route for weeks. Now, there's actually a work stream at the RSSB now, in the adhesion research group that we're part of, specifically looking at how you can improve freight performance in low adhesion.
It's a separate group, isn't it?
Yeah.
Chaired by our former chair, Bill Waddington. So it's a dedicated group, much like the TOC-based Network Rail infrastructure manager-based ARG, that now solely focuses on the problem that we've identified. It's worth just mentioning, so you mentioned 800s, so intercity services. Traditionally, adhesion is more acutely a problem with services with a more intense stopping pattern.
Yeah.
So in theory, the 800s are as good at stopping under low adhesion than any other train, but there's a strong argument to say they're probably not tested enough because they don't have to stop as often. So it's definitely, I mean, the northern networks that generally have the worst adhesion problems are ones that where the terrain is challenging, but also where the stopping patterns are very intense. And then you can bring in the different factors about gradient and
vegetation.
Indeed.
Yeah, it's quite interesting. We get a lot of grief off Transpennine Express because our trains cause them a lot. We're probably the biggest source of their delay in autumn. But I say to them, we'll change your name to Transpennine All Stations and you'll understand the problem. But it's a challenge for regional operators and
the best example to prove that this isn't a rolling stock specific problem is Scotland, because of course they run shortened HST sets over quite long distances, but at much slower speeds with similar braking patterns to what you might expect some of our DMUs to run on, and they've just had a significant WSP upgrade in response to some of the problems that they've had. So that puts it into perspective, I guess.
And also, just to swap further things, there's very different driving techniques with the modern locos.
Yeah.
Whereby the train is almost deciding itself what the adhesion factor is and so on.
One of the other things I forgot to mention.
Okay, as far as starting off is concerned, but not as far as braking.
Yeah.
That's traditional, really.
One of the other things I didn't mention with freight is there are certain poor sections that Network Rail try and implement what they call a clear route policy. So you hold a freight train until you know he's got a clear run through, so he's not going to get cautioned and then come to a stand. So that's something else we can do to try and improve them.
You've obviously, Andrew.
Roger, question for you, if I may. You left me a little curious with the conductive sand and insulated block joints. Is there an issue, or was it proved not to?
Oh, right, yeah, but no, we did some very specific testing to look at whether accumulation of particles where the end post is would cause a different problem for the track circuits. Ironically, we found the worst situation was the sand that's currently used when it's wet. So if you have too much normal sand builds up wet in that area, that was the worst case. So there wasn't a specific problem with the conductive particles.
Well, Salisbury somewhat provides some insight to that, doesn't it? With the resulting fusion of the wet sand and the significant amount of leaf matter to create, ironically, much slippery layer with the compound that resulted in what would have been there otherwise.
Yeah, so they're okay.
It's interesting, that.
Yeah. Well spotted.
Can't tempt anyone with any more questions. Okay, I've got none from home either. So just leaves me to say, Louis, Roger, Rob, thank you very much. Now, could I ask Mick to do the vote of thanks in the usual way?
Yes, thank you very much. It's an absolutely amazing amount of detail from people who obviously know what it is they're talking about. And Louis. We started the evening with Louis reminiscing about previous presentation and bringing us up to speed. And speaking personally, the most important bit I noticed from that was a map he had of the children's area, which actually showed Old Green, which is a little village halfway between High Wycombe and Amersham, which nobody ever heard of. It's actually my home village. But more importantly, we went on to so thank you to Louis for setting the scene. And then we went on to Roger, a vast amount of detail, and obviously an enormous amount of expertise, and thank you very much for that. Very interesting that Roger thinks the real world is tribology, but anyway, we'll gloss over that one. Absolutely amazing that leaves are actually better than the moon model. My goodness me. The fact that the different types of leaves behave differently is probably something that we shouldn't share with the media, or we'll certainly be castigated for years for talking about the wrong types of leaves. And water online, yeah, certainly that's obviously been known about for a long time. My history on the railway certainly was a vast amount of time in South Devon, and there you've got the line between Plymouth and Totnes, up over Dartmoor and back down again. Lots of mist, and the mist is what causes all the problems. You have heavy rain, and certainly heavy rain was not unheard of in South Devon. Heavy rain, no problem at all. So yeah, certainly the reality measures are there. And it's nice to know that sand works. I thought it was very brave of you to use a class 142 to test for track circuits. Bloody things used to disappear on the track circuits in reality on the real railway, let alone when you're trying to test them. Anyway, thank you very much. And finally, Rob, thank you for actually putting it into perspective of what it actually means on the real railway. And actually, it's nice to know that with all the problems that you highlight today, and 17 station overruns, that sounds a lot. 25,000 stops a day. Yes, that's not as we're doing pretty well, aren't we, really? So thank you very much. I like the idea at the end of Steve, actually. It's the reason for the amount of vegetation. Oh, no. So thank you very much, gentlemen, and please join me.
Thank you very much, Mick, and thank you very much to our speakers. Very interesting. That takes us on to our next meetings. Mick, your meeting?
Our next meeting is on Monday, 9th of February, and it's our annual competition for young members giving a presentation. If you know of any young member, we still have spots available for the competition. So just please contact me. We've got a whole year's worth of presentation or events organised. They're now on the computer. There is a download for a PDF copy. You can get the new PDF copy. I've got some printed versions here if anybody would like one, but certainly you can download your own from the website. So thank you very much.
Thank you, Mick. Richard, PWI next meeting, please.
Our next meeting is on Wednesday, the 4th of February, back at the Network Rail offices here next to Reading Station. It's about Old Oak Common, not all of it, but it's about level boarding for Elizabeth line trains. One of our members, Phil Holborn's, working on various works to make sure the platforms are the same height as the train floors. So that should be a most interesting engineering meeting.
Okay, thank you, Richard. It just leaves me to say thank you to everybody for making the effort to come along this evening. Thank you to those at home who tuned in. Can I please remind you, since we have some visitors online today, you need to leave the meeting, otherwise the recording system will carry on recording all night until you actually leave. So please make sure you actually press the little red telephone in the top right-hand corner, leave the meeting, and so that the recording will automatically shut down, because that is critical for the people who then have to publish the meeting online, because they then have to go through and edit it for hours because somebody has left it open. So please do that, and there'll be no hard feelings afterwards. And just to say, there were some comments made on the chat line. There's 4 listed here anyway, saying thank you very much, very informative in all different shapes and guises. So yeah, obviously the people at home enjoyed it as well, so thank you very much indeed. So just leaves me to say thank you very much, have a safe journey home, and we look forward to seeing you at the respective meetings next month. Thank you. Is it by magic? That's it by magic. Everyone has left the meeting.